Continuing on seawater for oceanography here. Obviously, seawater is quite an important part of the ocean. So here we are. The file running. Okay. There it is. Seawater. Of course, the water doesn't stay in the ocean all the time. There's plenty of evaporation. And so we have quite a lot of back and forth water cycle. Most of the water of the Earth's surface is in the oceans. Majority of the Earth is covered by water. But of course, we do have rivers, lakes, ponds, creeks, frozen water at the surface, glaciers. And then there's the groundwater. Water down below the surface in the holes and cracks and crevices. Groundwater actually is significantly larger amount than what's in the rivers and lakes, although not more than the ocean. And there are a lot of places where people are depending on wells, other groundwater sources for their water. So we have the hydrologic cycle or the water cycle. Water at the surface can evaporate, travel around in the air, eventually condenses, forms clouds, can fall as precipitation, rain or snow, maybe hail or sleet. Or you can have condensation on the surface like dew or frost. Now, of course, ocean being water, has a lot of evaporation. Land, well, yeah, we got rivers and puddles and whatnot, but a lot of land doesn't have much water on it. So, not surprisingly, most of the evaporation is over the ocean. Some of that ends up raining on the land and then eventually, whether through the ground or across the surface, making its way down and eventually back to the ocean once more. Maybe it evaporates first, depending on where you are in different situations. This picture illustrates many of those processes all going on. We have the ocean out here. There's a river flowing down into it. We have some clouds. And then we have snow. Looks like we've had some precipitation in the area reasonably recently. So highlights the importance of the cycling of water through the whole system here. As the water travels, it often carries other things with it. And so we have not just the water cycle, but many other cycles as a big biogeochemical system. Living things are involved, the rocks, the air, water all together. Weathering of rocks, some bits are dissolved, some are as pieces, gravel, sand, clay, silt. These get carried along. Maybe they get deposited, maybe they get used further by living things. Eventually, sand and mud on the bottom packs down, can become solid rock, lithified. And then plate tectonics, bring it around again. And now it's sticking up, bang, gets eroded. So we have these cycles that move materials through the various Earth systems. Measuring seawater, mentioned there's a little bit of a challenge if you just toss a bucket over the side of the boat and lower it and bring it up. Yeah, there's water going in now. Not the greatest way to try to measure something in particular. So you need to have something fancier. This is one such device. There's a Niskin bottle. You can lower it on the wire and then send an electric signal down the wire and that triggers the ends to close at a certain depth. And now you know specifically where you got that water from when you're studying the properties of it. Some other aspects of seawater. Seawater is salty, and we can't drink it. I mean, you can pour it in you, but largely due to magnesium, it's diuretic. You're going to lose more than you gain. So that's not good. Also, agriculture. Most of our crops do not like salt either. So desalinization is the process of getting fairly fresh water out of seawater. A common approach is distillation, where you evaporate water, leaving behind salt, and the condensation of the water that evaporated gives you fresh water. Again, salt doesn't evaporate under any ordinary conditions. Yeah, you can vaporize it in a volcano, but it's the water that's evaporating from the ocean, not the salt. Salt's left behind. So we can get pure water by distillation relatively easily. Freezing. We'll look more at that in a moment, but again, salt doesn't fit into the crystal structure of the water, and so it gets left behind. And that's another way to potentially make reasonably pure water. There are other things you can do, various types of chemicals to remove the salts. You can use electricity, certain types of membranes. It's kind of like the general idea of using sieve. Of course, the holes in the sieve are way too big to block the salt, but something with tiny molecular scale holes can let water through while keeping the salt out. For example, inside us, cell membranes can do that. Not that that's something we can very practically use as a large scale to produce lots of water for general use, but we can make membranes ourselves that are bigger than cell membranes with similar ability to let water through, but not the salt. Of these, using solar energy to power distillation of salt water is a very common method used to produce fresh water suitable for drinking or watering crops. Why would that tend to be a good method for desalinization? Well, where do you need water? Not where it's raining all the time. Instead, if you really need water, that probably means that the weather is usually dry and sunny, which means you probably have plenty of sun if you're needing the water. And so it's pretty easy to have the solar energy to do the desalinization. Now, bit of a problem. Once you've done that, you're left with very salty brine. What do you do with that? I mean, if you try it out entirely, you could sell it as sea salt. There's some potential there, but a lot of times it just kind of gets dumped, and then that extra high salty water is not great for the environment. So you do have some issues you need to think about there, but it is a useful way of getting water in places that need it. As promised, here's a bit more on ice with the oceans. Sea ice is ice forming by the freezing of seawater. An iceberg is not sea ice. Icebergs actually form when the edge of a glacier reaches the ocean or lake, and pieces break off of that and float away. So iceberg is not sea ice. Now, of course, it can be ice in the ocean, important that way. But sea ice is when we actually have seawater that freezes. Again, it's the water that's freezing and salt being left behind. We start to form small bits of ice. If it stays cold, they can grow into smaller clumps, kind of plate shape typically. And you get a slush at the sea surface that may, if it stays cold enough, long enough, build into more extensive ice cover. If salt's not in the ice, it's left in the water around. So that water gets saltier, which lowers the freezing point, makes it hard to freeze. So we're getting less and less likely to make more ice as it gets colder with our salt water. Over time, sea ice can get thicker, stays cold, snow may lean it on the top. More stuff can freeze on underneath, but still it tends to be relatively flat and thin compared to an iceberg. Ice sheets can be broken up. After all, they're on moving water, so currents and waves, wind breaks it up. Instead of icebergs, ice flows are the chunks from sea ice. As it first gets going, bits of ice washing around the ocean tend to bump into each other and get these round shapes. Understandably, this is referred to as pancake ice. Over time, however, it can potentially build up into a much more extensive mass of ice across the ocean surface, like this. Of course, you do have pieces moving around. They can break apart, collide together, colliding and pushing up some ridges there. Come apart, there's a crack, stuff can freeze in there. It's actually a little like plate tectonics, the way things work here. We can have divergent boundaries, things are moving apart, and new stuff freezes there. Convergent boundaries run into each other, push up mountains, and transform. One slides past the other. All that's going on. Of course, this is also rather important for things living in the ocean. The living things may actually hang out on the ice if they don't mind the cold conditions. And if you live on the ice, you need for it to be cold. With things melting, that can be a problem there. On the other hand, air-breathing organisms want water at the surface. This can be a challenge. You can have patches of water surrounded by the ice, and these become very important for things like whales and seals, seabirds, things of that sort. Seals actually may make a hole in the ice as it's starting to freeze over and keep coming back to make sure the hole stays open. And that way they've got a spot to come up and breathe. But that also means that the polar bear knows where the seal is going to come up. And so it can hang out there and then grab the seal when it comes up. And that's actually a pretty important part of polar bear food, which is why polar bears don't do so well if we have continuing global warming that melts the ice and the seals don't have to hang out any particular hole. Light in the water. Quite important for living things. How much goes in? There's a lot of variation. Not surprisingly, where the sun is it close to straight up in the sky or rather low down? Do we have lots of waves or is the surface pretty smooth? How much stuff is in the water? All these are quite important. We think of water as being transparent. That's pretty transparent, but you can tell where the water is versus the air. And there's a difference. It is absorbing some light. And in fact, in just 1 meter, over half the light has already been absorbed, converted to heat in the water. So you don't have to go very far underwater for things to be noticeably darker than they were up in the air. In very clear water, there's only about 1% of the starting light that gets 100 meters down. So it's going to be very dim in just 100 meters. Through air, 100 meters is nothing. If there's light around, you can see unless it's really, really, really foggy. But in water, 100 meters down is enough to be quite dark to our eyes. Different colors of light travel differently through the water. Red is absorbed pretty quickly. Blue is the slowest to be absorbed in pure, clear water. This is why things can look blue underwater. If you have very turbid water, turbid meaning lots of stuff in it, say maybe muddy, maybe it's plankton, whatever the stuff in it is, the water is not particularly clear. Light there may be blocked only 20 meters or less down. Tends to look somewhat more yellow to green because the particles are reflecting that, spreading it around a bit more. So you get a bit different look than the blue of clear water areas. Photic zone is the shallower water area, maximum about 200 meters, where it's very, very clear. This is where there is enough light for photosynthesis. Now, of course, the deeper you get, it has to be things pretty specialized, but there are a few things that make it down 200 meters or more, and very clear water is still able to photosynthesize. Some red algae can manage that, for example. Aphotic means without light. Now, if there's not enough photosynthesis, there still may be enough for sensitive eyes to see. You get a little bit of light enough to potentially be able to see something if your eye is good enough down to about 1,000 meters, 1 kilometer. Deeper than that, and basically the only light is from bioluminescence, living things, and any light produced, say, from volcanism and other undersea processes. Here's an example of its color differences. We have the Yangtze River flowing down here through China, carrying quite a lot of mud, or part of the way it's crossing an area with quite fine wind-blown dust, so that washes very easily. So a lot of it just looks brown, but then you see kind of more greenish look, and then as we get more into the open ocean, it's looking deeper and deeper blue due to the decreasing amount of turbidity from the sediment there. Sound in the water. Sound tends to travel faster through material that is denser. Higher salt, denser. Higher pressure, denser, and sound goes faster than those. However, sound travels faster with higher temperature. That's opposite of density. Sound waves are basically a pressure wave traveling through water. The water or air, like the sound waves that you're hopefully paying good attention to right now. It's basically kind of squeezing and expanding as the sound travels through. And so how fast the molecules are moving relates to the sound speed. And so higher temperature, molecules jiggling faster, you get the sound traveling quicker. Open ocean, slanty variation isn't too drastic. And so temperature and pressure tend to be our big factors in determining our sound speed for the ocean. As we go down the ocean, we'll see changes in those and thus changes in the speed of sound. Up in the surface layer, As we're getting deeper, there's more water on top of us, so more pressure. Temperature's not changing too much up there. Pressure's going up, so our sound speed is going up. Then we hit the pycnocline. Temperature's going down. Pressure's going up, but the temperature down, wind's out, speed of sound is getting less. Once we're through the pycnocline, we're down into the cold area, so temperature is not really changing. Yeah, there's a little bit of decrease, but not too drastic. So it's mostly just getting deeper and deeper. There's more and more water on top of you. Speed's increasing again. Okay, so we had speed increasing, decreasing, increasing. That's going to give us a low point towards the base of the pycnocline. Pressure and temperature adding up give us this pattern here. Sound being slower there versus to either side means that the sound waves can get trapped and travel across there. Now, up here in the air, we're used to sound waves traveling out in all directions, and the more they spread out, more dispersed, and pretty soon you don't hear the sound. But even here, we can do things to aim the sound more, and that keeps the sound together and louder in a particular direction for much longer. So sounds in the pycnocline, vast distances across the oceans, whereas above or below, the sound is spreading out more like we typically expect it to up here in the air. Why might that be a difference? What can make use of sounds traveling long distances in the ocean? Some ocean animals do, in particular, whales. Whales make sounds and travel long distances. So communication with other whales across long distances is potentially a useful thing to them. And so a whale can dive down into pycnocline zone and make noise, and maybe somebody on the other ocean, hey, Bob's over there somewhere. You've got potential for communication over quite long distances for them. Not too many other ocean animals are interested in very long distance communication, but one in particular, us. If you have a submarine, if you go down in the pycnocline and put out sound, it can be heard for very long distances. If you want to be heard, that's good. If you're a military submarine trying to hide, then that's bad. And you'll want to avoid the pycnocline as much as possible as you're traveling around. Sea surface. The very, very thin topmost bit of the ocean has some very important roles and distinctive aspects. Talking about only a fraction of a millimeter, barely visible distance here for the sea surface microlayer. Of course, that's what's touching the air, so anything going in and out between air and ocean goes through that. There are a number of things that live right at the surface. Living things are concentrated near the surface. Overall, the deeper you get, the less there is. There are all sorts of different back and forth things going on. Caption says it's a simple model, doesn't look like it at a glance. Zoom in a little bit more. Most of these are pretty straightforward. Okay, yeah, evaporation, bubbles, popping wind spray, bubbles rising, stuff dissolves, sinking, all that going on. Dry deposition, wet deposition, what are those? And the ocean's always wet, isn't it? True, but the air is not always wet. So wet deposition means when it rains or maybe snows, the stuff that carries down and takes into the ocean. Dry deposition is when you have things like dust or other material in the air that ends up settling down and going into the ocean without being washed in by the rain or the snow. Some examples of life there. This little, it's actually a true bug, is one of very few ocean insects. These skate around on the sea surface. You may have noticed similar ones that live on fresh water, skating around on ponds and creeks and rivers in our part of the world. You can find them pretty easily. You go down to the Broad River Greenway, for example. It can skate on the surface because surface tension, again, the attraction between the water molecules. That means that if water molecules can stick together, light enough weight can skim along the surface and not sink in. Couple of floating animals here. We have on the right, this is a by-the-wind sailor jelly. It's not a true jellyfish, it's actually hydrozoan, but broadly related group there. It has a float with a little sail drift around on the ocean surface. This one is being eaten by a xanthinus snail here, purple snail. The snail makes a bubble raft here. And by hanging onto its bubble raft, it keeps from sinking. Otherwise, the shell would be heavy enough to keep it going down, but thanks to its raft, it can float around, and it eats things like by-the-wind sailor, or may even munch a bit on a Portuguese man-of-war here. This is another hydrozoan jelly, not a true jellyfish. You can see it has a soft float here, and then long tentacles hanging down. Portuguese man-of-war has sting that can be quite painful to humans. Potentially, if you were swimming, got badly tangled up in it, you could possibly die, partly because if you're out in the ocean and are starting to have health problems, you've got the added risk of drowning too. Portuguese man-of-war is something to keep an eye out for when you're at the beach, because they do wash up. Portuguese man-of-war don't have any way of steering. They're just floating, drifting with the wind and currents. And so they do sometimes wash ashore like this one has. Along with that kind of blue-purple float, you can see some of the tentacle there. Again, they have powerful stings. And the stinging is not directly controlled by the jellyfish. It doesn't have a brain to do the controlling anyway. Anything touching it triggers the sting. Still works after the jelly is dead. And a somewhat dried up tentacle is not easy to see on the beach. So seeing a float like that, you do not want to get too close to it to avoid running into stingers. This particular one's in Alabama. There's also one time I was in Florida, actually Key West, seeing a bit of a beach. Can I go down there and look for shells? And then as I got closer, the beach was covered in Portuguese man-of-war float oats, and no, I'm not going to try looking for shells there. Important things going on with that thin surface microlayer. Lots of living things there. the bacteria, plankton in the water. And of course, then that's where those are. So the things eating those tend to be concentrated up there as well. Some important chemical things going on. Photochemical effect. UV light has higher energy than visible. That's why it can give you sunburns and skin cancer and all that. But UV is absorbed quite quickly by water, so it doesn't penetrate very far in at all. With that high energy, it can trigger chemical reactions, like the chemical reactions in your skin when you get fried by it, but also chemical reactions in various substances that can be floating around the water. And then once those reactions happen, the stuff can mix in with the water. So even though UV is only penetrating the very surface, the effect it has there impacts stuff through much more of the ocean. And again, it's where you have the direct contact with air. So all the back and forth that goes on between the atmosphere and the ocean involves a surface microlayer. Okay, so summing up on seawater. Water molecules are polar. They have positive and negative in different parts, and those opposite charges attract. So water molecules tend to be attracted, kind of stick together. This gives water many properties such as the higher melting point compared to similar chemicals, the higher boiling point, the ability to dissolve a wide range of substances, the high heat capacity, and the way it's actually denser as liquid than as ice. Seawater, of course, also has salt, average about 35 parts per thousand. The major components are in constant proportion through the oceans. So the relative amount of things like the chloride, the sodium, magnesium, the sulfate, calcium, potassium, those stay consistent throughout the oceans. Now there may be a little more water, a little less water, but the major parts of the salt, the amounts compared to each other stay the same. Because seawater is salty, melting point's lower, boiling point's higher. Long term, about equal amounts of salt are coming in through processes such as erosion and being lost through, say, chemical reactions with the sea floor, what's left behind by evaporation, similar processes. Different properties of different parts of the sea lead to producing layers. We have temperature differences that can set up thermoclines, salinity differences, haloclines. Either of those is a type of pycnocline, a density difference. Pycnocline zone, being isolated from above and below, tends to have lower oxygen, drop in temperature, gives slow sound there. The deep ocean regions, the water there is relatively cold and dense throughout. Light, surface temperature vary quite a bit, different parts of the ocean, and we have those important properties of the very surface of the ocean and how that interacts with the air. And that wraps up Chapter 5 on seawater.